Hello, everyone. This is where we start actually doing lecture videos and working through problems and such. I'm recording this currently while also in office hours, so it may halt, start and end up starting a new video. Um, I'm just trying to be efficient with my time because no one has checked in. Anyway, this is introduction to vectors. This is y'all are looking at this, and most of you probably haven't seen anything like vectors before. Maybe a few of you do computer programming. I don't know, but what I want to go through is kind of some definitional things in this video. I've used some scary words up here: scalars and vectors. Scalars, the reason it has that word will make sense in a little bit. But generally, we're just dividing all the things we can measure into two groups. And one group are the scalars, and they're just numbers. Anything you can measure where the only thing you can put with the measurement is a number, that is a scalar. Things like mass and temperature, speed, those are things that are numbers. I'm sure there's several others: volume, area, length. Counting things, those are scalars. If you're counting like a number of books, that's a scalar. Now there's another set of things where what does matter is where the thing is pointing in some way. There's some sort of direction associated with the measurement, and that's what we call a vector. And we got some examples. One is velocity. If you're driving somewhere and you drive 60 miles an hour, it also matters where you're going. If you drive 60 miles an hour north up the interstate, or if you drive 60 miles an hour south, those have completely different meanings. Force is another one. For one example is weight. Mass is just how much stuff there is. You get on a scale, it gives you an indication of how much of you there is. But weight is a force. It has a direction. And in this case, it's toward the ground. You get on a scale, and it tells you how much you're pressing downwards on scale. There's a few others. When I mention length and area and volume as scalars, there are versions of those for vectors. What's called the displacement here is how far away are you from some starting point. Right? If let's turn on annotations, good. Like let's pick a point here. That's where you're starting from. And it matters if you're going to go 3 or 4 inches over. Right? It matters if you go to the right. So we put an arrow in. Or it matters if you go the same distance up and to the left a little bit. And it also matters, in a sense, where you start and where you end up, but it doesn't matter how you get there. All right, this path results in the same displacement, has the same arrow, and this one results in that displacement. All right, so certain measurements, we can put a direction with them, and what's going to matter is the size of the measurement, what the number is, and some sense of direction. And so those are scalars and vectors. So when we want to represent a vector, we use arrows. We start it at some point. We start it there. and we draw it for some length that represents how big it is, what the magnitude is. And it goes to some endpoint, which tells us which way it goes, right? And so here are two vectors, A and B. They represent velocity. If you're watching if you go tonight and watch the 6 o'clock news and watch the weather, they will often have a map that tells you wind speed. And on that map will be a bunch of vectors, a bunch of arrows, and some of the arrows will be longer than others, and they'll all point in some direction, starting at some location. And if you look, you can find your location, and you can see which way the wind's blowing. And it'll tell you how fast it's blowing by how big the arrow is. They'll also give you a map that has temperature on it, and temperature is a scalar. It just tells you the number value. There's no sense of direction with temperature. But we have these two vectors. They represent some sort of velocity. It's some rate at which you're moving in some direction. And so A here is 5 meters a second. So you can imagine this is a brisk run or jog. You're jogging across a room or down a hallway, 5 meters a second that way. Twice as fast as B, and you can see it's twice as long. So there's another way of representing vectors, and you might recognize this sort of thing from your math classes. When you had coordinates, and we'll use coordinates in physics, when you had coordinates, we had X and Y, but you also had R and theta. You had polar and rectangular. Well, there's a sort of version, this can be expressed either way. It can be a certain amount to the left, a certain amount to the right, and a certain amount up. In this case, it would be 3 meters a second to the right and 4 to the vertical direction. But you can also express them as an angle, turn a certain direction, then walk a certain distance. And so we can express it in those polar coordinates the same way we can express it in the rectangular coordinates. And so you can think of this a little bit with these vectors. Put one end of it at the origin, and then the coordinate of the other end tells you some information about the vector. And so you can express them like this, or you can express it, put the beginning of the arrow at the origin, and then turn the arrow in some direction and draw it for a certain length. So that's what I'm talking about in terms of these coordinates. We can express the portions of these vectors as extents in some direction. And this is the thing, is that we have these vectors, and they're arbitrary. A vector that I've drawn here that's 5 meters a second on this slide there is the same as this vector that's 5 meters per second in the same direction. The location doesn't matter. All that matters is the length of it and the direction. So this vector that we have drawn here, it has some extent, and we can make any two vectors add up to it eventually. But what we do is we pick the ones that are along our axes, along the x-axis and along the y-axis. Right? And so because the axes are perpendicular, y is perpendicular to x, then there's a right triangle here. And we can use that right triangle and use the angle that we might know to find what these components are, how far up, what coordinate is up here, how far in the x-axis, how far in the y-axis. And so we use our trigonometry. These coordinates look like the hypotenuse of this triangle, A, times cosine theta, and in the y direction, it's A times sine theta. Now, we're going to practice breaking a vector down into components and then adding up the components to make a vector and going between the components and the length and direction. So this is how you get to components. If you have the length, the 5 meters a second, and the direction, the angle theta. Okay. And when I'm talking a little more about, the x and y components are parallel to the x and y axes, they're perpendicular, and they add up to the vector. Now, I will have another video in a little bit where I talk about this sort of map direction thing. Instead of having x and y, you can have north and east, or south and west, or however. But the point of it, and if you go enough into other math, you can find that you can define coordinates that aren't perpendicular. You can warp your x and y axes. Right? These vectors are a mathematical object, and I've given you a document in your packet that goes into some more detail about this. It goes into it as physicists do, but it goes into some of the underlying stuff about this. This is when you get these videos, the goal is to give you an operational definition of everything. This is what you need to do to get through the homework. The other documents that you might see, they're further out. They're how do these things work? Why are we doing math here instead of just defining terms? Right. So anyway, these are components. You can define them in various ways, but in general, they're always going to form right triangles. And they're going to form right triangles such that you know the angle and you know the hypotenuse, or you know the components, or maybe you know some other combination. If you know the angle and one component, you should be able to build the other two components. This is all the stuff you were doing in your trig classes with sines and cosines and tangents. Okay. So the whole point of defining these vectors is to have some intuition about adding measurements up or doing math on measurements where you have direction involved. So imagine you're driving to school, and for this, let's say it is a drive that I'm going to make. I'm going to drive from my home to the governor's school, and then I'm going to drive from the governor's school to Radford University. That's a drive I have to make often. I teach down at Radford, and it is a long drive. So say it's 20 minutes to drive to the school, and the way I drive, that makes it about 15 miles. And it's also 20 minutes to Radford, and it's about 15 miles there. Now, the naive way of thinking of this is to say, well, I'm driving I'm driving 15 minutes. So, I drive from home to the governor's school, and then I drive for the 15 miles to Radford. And so that's 30 miles I've driven. And that's true. The odometer on the car would say 30 miles. But I'm not 30 miles from home. All right. The displacement that I would have is represented by r, which is this black vector, which I need to, it's represented by this vector here. And that is my displacement. And it's not 30 miles because the return trip, when I drive home from Radford to home, is also about 20 minutes, about 15 miles. It might be a bit more. 20 minutes, but it's on the interstate. So it's 20 or 25 miles. Right? So we have to encode the directions that I've driven in it. And so a way of adding vectors up is to say, we're going to align the vectors up head to tail. All right, we draw one vector A, and then at the end of A, where the arrow points, we immediately start drawing B. And that's going to tell us the sum is going to be represented by starting at the beginning of A and going to the end of B. And we can do this because it doesn't matter where A and B are. We can, and now I'm going to turn on these annotations and try to draw. We can draw A off to the side over here, but we can also draw B. So there's A and B. And then if we draw the result in, it is fairly, it should be the same vector. And I go into detail in the other notes, is we want an object that works like numbers. If I take 1 plus 5, that has to equal exactly the same thing as 5 plus 1. If I have one object and 5 objects, 1 apple and 5 apples, or 1 cat and 5 cats, I ought to have 6 cats no matter how I arrange them. So you could imagine that the drawing I've made in the annotations could be that I've driven, instead of driving to the governor's school, I drive to, does anyone know where Hiwassee is, or Indian Valley maybe? I drive somewhere south towards Floyd. And then I drive to Radford. And that should represent roughly the same displacement, though I'm taking these directions and I'm driving, out of order in a sense. I'm driving on a different path, but I should get the same displacement. All right. So this gets awkward afterwards. You can do it for 2 vectors. You can do it for 3 vectors, but there's not an unreasonable likelihood you might need to do this for so many vectors that it becomes unwieldy. Right? You might need to throw it at a computer and make a computer do it. And you would like to have a representation where you don't have to draw, right? Because you can see how I drew. That was horrible. So you want a new representation. Anyway, I'm going to stop the video here so that we can start over again with addition and subtraction and doing the math. So this is going to stop the video.